Hi, welcome to another video. Today I'm looking at the safer option for a battery wall. In case you're running solar panels and you want a battery wall and you want to build a battery yourself, this is a safer option. These are LiFePO4, so Lithium Iron Phosphate. Why do I say the safe option? In case you haven't seen the news for the last decade, regular lithium iron cobalt batteries catch fire. Ask Elon Musk, he'll tell you, and here's some pictures. Pictures of some car fires and a picture of their mega battery pack in Victoria, Australia, where my twin brother lives. So I went for this option, capacity 50 amp hour, so I can consume 50 amps for 1 hour before this one cell is flat. It's got an internal resistance of 0.37 milliohm, and in case you want to know the weight, 1,328 grams per battery. They don't have a positive and negative marked on them, but the QR code is actually on the negative side of the battery. If you get that wrong, if you start connecting these links to give you 12 volts, you'll start burning these links if you get it wrong. And I did one morning before I had any coffee, before I woke up. And these are slightly heavier than the equivalent lithium iron cobalt cell. But to make one of these, out of these, I would need 25 of these. I would then need the strips welded on the top, welded on the bottom, then package them. And I'd also have to buy a welder because I don't have a spot welder. So I went for the simpler option. So this video is really for beginners and an introduction into lithium iron phosphate cells in case you're totally unfamiliar, or maybe you're just totally unfamiliar with batteries altogether. I'll put the link in the show more. These batteries are from eBay and they're £55 each, so they are more expensive than lithium iron, and they are a lot more expensive than the equivalent lead acid. But I'll go through some of the lead acid details later. A lead acid battery, you are only meant to discharge by up to 50% of its capacity, and then you can only cycle it like that roughly 400 times. These batteries, you can actually fully discharge them. The manufacturers say if you discharge these to 90%, you can reuse them 4,500 cycles. 3.3 volts isn't going to drive a 12 volt inverter, so what do? Join them all together in series. So with these mounting plates, you have to put the batteries side by side. So if I turn one around, that one like that. So in series, this is positive, negative, negative goes to positive. Then over here, negative goes to positive. Then the last one, negative goes to positive. Now if I put all the nuts on, now that these batteries are connected into series, this is the positive, that's the negative. You've got to concentrate when connecting these bars. If you get it wrong, you'll melt something and burn your fingers. So let's see what we have with this meter. 14.67 volts. And consume 50 amps for 1 hour at 12 volts before all these batteries are flat. So if they're 50 amp hour, and I've joined 4 together, why can we not have 4 times 50, sort of 200 amp hour? It doesn't work like that. We've just gained 4 times the voltage by connecting them in series. I'll show you a picture. We can't have 4 times the voltage and 4 times the current in this configuration. We've just simply multiplied the voltage by 4. So what if you want double this capacity? You would simply get another 4 batteries and join the 2 negatives together and the 2 positives. Then you would double the capacity to 12 volts at 100 amp hour. Right, so I've removed the links. I'll measure each battery now, but I'll go into details later. So each battery, when they're fully charged, Remember, negative is with the QR code on that side. 3.67. These batteries, the maximum charge voltage is 3.65. So these are a touch over 3.65. 3.67. 3.67. 3.64. And finally 3.67. How do we get 4 times this capacity? You simply join them all in parallel. I'll put that one there, and there aren't enough brackets to put all these 4 cells in parallel, so I could simply put these bits of copper wire, thick copper wire, under the nuts. If I was to screw all these down, put all these nuts on, I would then have 3.2 volts, and I could consume 200 amps in 1 hour, or consume 50 amps for 4 hours, since I have 4 batteries. So I've quadrupled the current capacity by putting them in parallel, but I've cut the maximum voltage in 4 because they're in parallel, not series. Right, so I drew this earlier. So Lithium Iron Phosphate Battery Basics by me, John B, 28th of May 2022. So you've just seen on the bench, we connect all 4 batteries in series. We get approximately 12.8 volts, and as I mentioned, we can consume 12 volts at 50 amps for 1 hour. Each battery, nominal voltage 3.2 volts. 3.2, 3.2, 3.2, 3.2, that's up to 12.8. Then you saw I connected the batteries in parallel. So we've still got 3.2 volts, 50 amp hour, but all 4 connected together, we can then multiply the current and increase our capacity by 4 times. So we've still got 3.2 volts, and as I said, we can consume 200 amps for 1 hour, or 3.2 volts at 50 amps for 4 hours. The important thing with these lithium iron phosphate cells is the charging current. You charge at a constant current. So with these cells, the minimum cutoff voltage is 2 volts and the maximum cutoff 3.65 volts. But if you look at this charging, it took me approximately 8 hours to charge the batteries, and the voltage only went from 3.4 to 3.5 volts. But what's important is this bottom end and this top end, and I've done plenty of tests. Once the battery gets above 3.5 volts, it takes minutes to shoot up to 3.65 and over, and similarly with less than 3.4 volts, it takes tens of minutes to get from 2 volts to 3.4. It's this long, nearly flat line between 3.4 and 3.5, which is where all the chemistry inside the battery happens. That was charging these batteries with 2 power supplies that gave me a constant current of 7 amps. Once the voltage has got to 3.65 volts, you can actually turn off the constant current and just leave 3.65 volts on it. So 3.65 times 4 equals, once each cell is up to 3.65 volts, 14.6 for the 4, you can actually leave 14.6 volts on the batteries and let the current drop down to nearly nothing. But in my experience, that actually only takes minutes. The battery manufacturer for these batteries here say you can charge the batteries at 50 amps constant current. So ideally, when you charge the batteries in series, you would expect to find 3.65 volts across each cell. But that doesn't actually happen in real life. And I've experienced it just with the first charge. The first morning, one of my batteries was overcharged, and it's something like this. 3.55, 3.65, 3.45, but 3.95. Now that 3.95 isn't much above 3.65, but the battery manufacturers say that the maximum is 3.65, so this one here on the right has effectively been overcharged. So because of the discrepancy with the voltages across each individual cell, you really should look out for a lithium iron phosphate battery management system. But you need to look at the specs of the battery management system and see what does it do for your money. I'm actually going to design and build one over the next few weeks. I'll use a microcontroller, and a microcontroller can easily look at 4 voltages and shut the battery off or start putting a load on the cell should it need to discharge it. So this is a recap. 12 volt lead acid batteries are only meant to be discharged to 50% of their capacity. When you do that, you can cycle them approximately 400 times. For manufacturers of this specific battery, you can discharge to 90% and still have over 4,500 cycles. The battery capacity, 50 amp hour, so the C is the capacity. Charge at 1C means you're charging at 50 amps. Discharge at 1C, so you discharge at 50 amps and they should last for 1 hour. The battery manufacturers say you can discharge these at 3C, so per cell that's a massive 150 amps per cell. The only way to test do the cells match up to the specifications is to put them on an electronic load and discharge one over a given time, and that's what I'm going to do. I'll show you. I'll test one at 0.5C, so discharge just one cell at 25 amps and we'll see how long it lasts. Then I'll do another one at 0.2C, so 10 amps, and see how long that lasts. Right, here we go. So negative, get that one first so I don't blow up my electronic load. I'm sure it would be better if these pads were painted. Positive. Tighten them up because I'm going to be drawing 25 amps off this first one. This is a Tenma electronic load, so if I go constant current, adjust the current, 25 amps, so it's half C. 25 amps, enter. Hopefully you can see that from there. So it's connected to the battery. Start this current consumption, 25 amps. The noisy fans come on, which is a shame. Just the way it's balanced, I guess. You can see that's quickly dropped to 3 volts. In fact, what I'll do, I'll pause this for a second. What I should have done, this electronic load comes with PC software and it's got a battery test function, so I can tell it to discharge current 25 amps, and I could tell it to cut off at 2.000 volts. I'll leave the discharge capacity 100 amp hour, but then discharge time what shall I put? 99999 seconds. So 25 amps should take 2 hours. So let me see. 60 seconds times 60 equals 3,600 an hour, times 2 equals 7,200 seconds. So yeah, I'll leave this 9999 seconds, otherwise it cuts off in time. And then hopefully this will count the seconds, so I can do a battery test here. Right, so I'm now connected. My battery start. There we go. There's the current shot up to 25 amps. There we go, had to refocus the camera. 25 amps, the battery voltage down to 3 volts. That's how many watts we're consuming. So that's the set figure, and that's the actual current here. These key buttons are now locked from the PC, so I can now leave this and come back near 2 hours to see what it's doing. Here's a look at the progress. When this reaches 1.8, that's 1800 seconds, we should be at half of 25 amp hour. So this should be 12.5 amp hour, and the voltage has just dropped to exactly 3.000 volts. So remember, I'm discharging at 25 amps per hour, so this should be 12.5 in half an hour. There we go, that's half an hour, 12.5 amp hour. And you'll have to forgive me holding the camera. That's the battery voltage at half an hour, and there's the tester. I'll come back in another half hour. Right, we are approaching 1 hour, so this should be 3,600 seconds, 1 hour, and we're approaching the 25 amp hour, which is what I set. 3,600 seconds, and there's our 25 amps per hour, and the voltage 2.9758. We are approaching 1 hour 30 minutes. This will get to 5,400 seconds, and this should be 37.5 amp hour. So 5,380 seconds, 5,390, 5,400, so that's 1.5 hours, and 37.5 amp hour. So 12.5 amp hour every half an hour. So we're on track for the 2 hours, and the voltage, the all important voltage, there we are, 2.9370. There's a few minutes left on this before we reach 2 hours. So I've noticed the battery voltage 2.8, and it's starting to drop faster. So if I let you watch this last 4 minutes, so we're up at 48 amp hour at just under 2 hours at the moment, and you can see this voltage is falling quite quickly. So at 6,990 seconds, 7,200 is 2 hours. As you can see, at that voltage, the watt hour we're consuming is dropping. I noticed it stayed at 2.9 something for a long time. Then once it got down to 2.8, it started to drop quickly. So that's 7,040 seconds. We're at 48 amp hour. The manufacturers quote a 2.0 voltage cutoff. Any more than that, you potentially damage the battery. .49 amp hour. Got 7,100 seconds, so we're nearly at 2 hours. So it's not a bad battery, is it? 25 amps for 2 hours. My little lead acid batteries in my UPS uninterruptible power supply, I think they were 7.2 amp hour. In one of my UPSs, it's 7.2 amp hour. So 7.2 amps, 1 hour, that's it, it's flat. We've had 25 amps for 2 hours, and this is still going. So 2.7 volts times 4 batteries, we would still have 10.8 volts. So a lot of inverters would start to cut off near 10 volts. You can see that's dropping rapidly now. We are at 49.7 amp hour. .8 amp hour, 49.8 amp hour down here, right, that is now 50 amp hour, 7,200 seconds. So that's now over 2 hours. So consuming 25 amps for over 2 hours at the moment. I guess since I've come this far, I may as well leave it on to see when does this drop to 2.0 volts. And the battery on this camera is down at 19%. So which is going to come first? Is this going to get to 2.0 or is my camera going to go off? We are at 51 amp hour. But obviously at 2.3 volts we've got 9.2 now if there were 4 cells joined in series. So if your equipment is voltage sensitive, then this is important. There we go, it's finished. And notice the battery voltage is creeping back up again. So it's not fully discharged. Back to the discharge curve. I imagine discharging the battery with 3C, the curve is going to come down sooner. I'll put the link for the batteries in the show more. He does ship to Europe. I found these cells to be the best value for money with capacity and no messing about having to weld a load of these together. So that's the battery. Have a look at the link. Hopefully you found this video educational. Don't forget to click like if you liked it. Thanks for watching.